All right, we're now recording. Let's get the slideshow set up from this current slide, and we'll go from there. Now, you can turn on the projector. Any questions on anything we've done so far? Those who've looked at the test, okay, in that regard. If you do have questions on the test, especially if they're clarification questions, what are you really asking for? What does this mean? Or are you sure this number's right? I'll answer any of those, of course, anytime. But if it's, I don't remember doing this, or, I remember doing it, but I don't remember how, find an example, a problem like it in the book. Like it, not the same one, if it happens to be the same one, and I will do anything from the book as long as it's not the same problem, or too close, okay. But you can usually find something that's pretty close. All right, no questions? One of the last little topics in here before we move on to out of separation of variables, solutions defined by integrals. You may have situations that you separate the variables, integrate both sides. Maybe you can integrate one side, but the other side, there's no way to integrate that. And that happens. What do you do then? Typically numerical integrations, okay? And that does happen, or you can just leave it in the integral and let someone else figure out how to integrate it. If g is a function continuous on an open interval I containing some value a, then for every x in I, let me get my pen activated again. There we go. And this is from what? Fundamental Theorem of Calculus Part 2 maybe. D by dx times the integral from a to x of g of t dt, that is g of x. I think that directly from Fundamental Theorem of Algebra, part 2, I'm pretty sure it is. That's the definition of g of x, It's the derivative with respect to x of the integral from a to x, any constant to x, of g of t dt. That's how we define g of x, okay? Now, you might recall that in the foregoing results, I guess that one I just wrote, is one of the two forms, of the Fundamental Theorem of Calculus. In other words, the thing in the integral there is an antiderivative of the function g, okay? And if you take the derivative of an antiderivative, you get the g, okay? There are times when this form is convenient in solving differential equations. For example, if g is continuous on an interval I containing x0 and x, then a solution of the simple initial value problem dy dx equal g of x, y of x0 equal y naught, that is defined on I is given by, and you can give that solution, y of x is equal to the y naught, okay, plus the integral from x naught to x, as long as they're both in the interval in question, g of t dt. Now that doesn't look like a lot of a solution, does it? But the point is, sometimes that g of t is something that's very hard, if maybe not impossible, to integrate. That is a solution. And you can do numerical integration on it, and they have computer packages and programs and stuff that will do that, and then you can come up with an approximate answer, okay? You should verify that y defined in this manner does satisfy the initial conditions. Okay, now remember what was our problem? They said dy dx is equal to, just saw it, there it is, g of x, and y of x0 is equal to y0. Okay? Well, if that's your solution, then to get from here to there, you do dy dx. And that's equal to dy0 dx plus d by dx of the integral from x0 to x g of t dt. You just taken the derivative of each of those terms. Well, what's dy0 dx? What is this one? Derivative of a constant. No, derivative of a constant. Y0 is just some number, a constant. What's the derivative of a constant? 0. That's a 0. Well, what is d by dx of this thing here? Isn't that exactly what we have up here, where a is x0 in this case? That would be g of x. And guess what? You got dy dx is equal to g of x. Yes. Now, really, the initial condition really didn't come into play because the derivative of that was 0. So, it looks like we ran around in a circle, and that's sort of what it feels like. So let's do a real problem that way, or as real as it gets in this text. Okay, we'll erase all that ink, and let's do this one. Solve this. Dy dx, okay, is equal to e to the minus x squared. Okay, as long as y of 3 is equal to 5. How would you go about solving that? What's the title of this section? Huh? A little louder. Separable equations. So how would you go about solving this? Hint, hint. Try to separate. And how would you do that? Write it in differential form. dy is equal to e to the minus x squared dx. Done. You got all your y's on one side, all the x's on the other side. No y's on the x side, no x's on the y side. And now what do we do? Now we integrate. Okay? And what's the antiderivative of dy? Y. Okay? Now, antiderivative of that. I don't know it, and I don't know any technique to solve it. Period. Okay? Do you? I can't think of a substitution that will work. Integration by parts. Nothing. So, what do we do? Okay? We leave it in that form, okay, basically. By the way, when we integrate this, we're going, because we don't have the values we need, here's the trick, okay? And this seems like you're playing games, but you're really not. We're going to introduce a dummy variable on both sides, okay? That dummy variable over here, we're going to do dy dt dt, okay? And we're going to run that variable t from 3 to x, okay? So that will give you y as a function of x, okay? Now, we'll come back and do that in a minute. So let me erase this for now, though it's going to come out the same thing. Okay, now what we do on this side is very similar. We change the x's here to t's. Okay. And run the t's from 3 to x. So that's e to the t minus t squared dt. Okay. Now that basically is exactly like what we had before. May not look like it, but that is the same thing. Okay. Now, as you said before, the antiderivative of this thing is just merely y as a function of t now. Okay, no, well, is as a function of x. We'll put t for now. Evaluated from 3 to x. Okay? The integral of the derivative is the argument of that derivative, the y. And over here, we just leave it alone. Okay? The integral from 3 to x of e to the minus t squared, because we don't know how to integrate that anyway, and we'll just leave it like that. Okay? That's having what they call solutions defined by an integral. That's going to be part of your solution. The only thing we have to do to complete this is this. When you evaluate the t at x, these values, it's going to be a y of x minus y of 3, and that's equal to the integral from 3 to x e to the minus t squared dt. We're not going to change that. But we know what y of 3 is, right? That's 5. So this is going to produce y of x is equal to, I've got an itchy nose, I must be going to have company, okay? Just kidding, okay? Is equal to, I'm sorry, it's minus 5, so I'm going to move the 5 over here. 5 plus the integral from 3 to x e to the minus t squared dt. There's your answer. Okay? And that's exactly what they get. Now, was there any real reason to go through all that dy, dt, dt? I can't see any. What did we do before? We just said this is y. Okay? And then we said, and let's just do it this way. That would then be y is equal, and you could say y of x, that's the only variable we have so far, is equal to, and this is how I would do it. We integrated here and had 3 to x e to, now you have to do this part here. You have to put in the dummy variable t. Okay? But then we put in a plus c. Okay? And then what we would do is evaluate this at x equal 3. Because that's what we are doing here. Okay? So, y of 3 would then be the integral from 3 to 3 of e to the minus t squared dt plus c. What is an integral from something to itself? 0, because you're integrating that much, nothing at all. So this is 0 from 3 to 3, and y of 3 is equal to 5. So 5 is equal to c, so you just plug that in, and you get y is equal to the integral from 3 to x e to the minus t squared dt plus 5. Same thing we got before without having to do this mess, which I find really an awkward way to do. Just leave that as an integral of dy, that's going to be your y. Forget about that, it's going to be y. Put a plus c on the other end, evaluate it at the value you know, and you got it done. Okay, so I don't know why they put in that step. Wasn't much, does the same thing, but it's just so hard to justify. What do they mean by that? Well, yeah, technically it's right, but what's the point? All right, So, this last example, as we've seen here, some simple functions do not possess an antiderivative that is an elementary function. Integrals of this type are called, guess what would we name them? Non-elementary functions. Boy, pretty creative, aren't they? So this is 1, e to the minus t squared dt, the integral of that, non-elementary. Sine of x squared, not sine squared of x, but sine of x squared. No way to evaluate that. That's a non-elementary function, integral, okay? That was the first remark here. The second one, in some of the preceding examples, we saw the constant of one parameter of solutions of first order differential equation can be relabeled when convenient, also blah blah. I'm not sure that is going to be anything that we have a great deal of interest in, so I'm going to skip that one. It's just a remark at the end. If you need it, go for it. Homework exercises here. Any of the odds 1 through 21, a whole passel of those, or at least half a passel anyway. Then any of the odds 23 through 27. Then do 29. Do either 31 or 33, or both if you choose. Do any of the odds 35 to 37, either 35 or 37, or both. Any of the odds 39, no, either 39 or 41, or both. I'll let you choose that. Do 43. Try to do 43. Any of the odds 47, 45 to 49. And then there's some discussion problems that you could look at some of those and, think through them. That's not going to hurt you, but, up to you. Then there's some mathematical modeling. We haven't done much of that directly, but if you want to take a look at that, this is summation bridge, actually that was my last class. We saw an example of that. It wasn't this class. I was going to say, we just did that, didn't we? So I doubt if there's anything, but you can look at some of those if you're interested in pursuing something else, go for it. So we've done the separable problems. Now this book doesn't quite do the same order of what my work study student found in old, or looked on the internet or something, Cameron, he found somewhere, and let's see, yeah. What they used was something called shield. Okay, the S was separable. Okay, and then the next one was homogeneous, I'm pretty sure. The next, I'm pretty sure, is integration factor. The E, I know what that one is, but it's flown the coop right now. But the L was linear. Okay? This text is going to linear next. It really doesn't matter. You don't have to do it in this order. And D, I think I know what they're talking about there, but I can't think of the term for it. So you don't have to follow the same order as shield, but we will be doing some of that stuff as we go. So if that's something that's helpful to you, I don't see how it could be, but you feel free to, and you may find that somewhere else. And I may remember what those other letters stand for. Anyway, let's move to linear equation. First, a definition. The form of a linear first-order differential equation was given back in section 1.1, and I'm going to repeat it now. And this is a first-order linear differential equation. Here's the form they're going to use here. A sub 1 of x dy dx plus a sub 0 of x, y, why not, is equal to g of x. Okay? Now, for a long time, that's going to be our equation 1. So sort of get it in your mind. That's a standard classic form for a linear differential equation. Okay? Now, what do these things mean? The only places you have y's are in the first derivative, because it's a linear first order differential equation, and the function y itself. So the derivative of y and the function of y. That's where the y's go. You will have to be able to get those on one side of the equation. Now, they can have coefficients that are functions of x. Not just a coefficient number, like 7 or 14/3 or something like that, but this could be a function of x. That could be a function of x. And then on the right-hand side, when you get all the y's on this side, you can still have some x's over here. That's your basic form for a linear first-order differential equation. Okay. Now, that's said to be a linear equation, first-order differential equation in y. Okay. Now, that's what I think was referred to back in 1.1. We're going to change that to a standard form. This is a form, okay? What I'm going to do here is divide everything on both sides of the equation by a1 of x. Okay? What you do, you lose the coefficient here. So now we have dy dx is equal to some new function of x. And I kind of regret that they call it p of x, capital P of x. Because when I see capital P of x, what do I think of? What do you think of? P of x. Anything come to mind? Capital P of x. I think polynomial function. Because that's what we always called. If we had another one, we call it q of x. But we put a capital P or capital Q, and we could do more if you wanted to. This is not a polynomial function. Obviously not. It's a rational function in x because it's a ratio of a0 to a1. That's not necessarily going to be, and guess what? Either a0 and a1 didn't have to be polynomials either. So this is not a polynomial. It's just some p of x. Okay? Times your y. And then this is equal to, and then rather than calling it g, let's call it f of x. Again, the odds are it could be a rational function or it could be any old function. But it is only a function of x. Oh, you let me do that? Someone, y'all need to wake up here. Okay? That's plus, not equal. Okay. dy dx plus p of x, y is equal to f of x. That's a little simpler. Rather than having 3 functions of x, you only have 2. And you have the dy dx by itself. You think this is separable? In general, no. There's no way you can separate these two easily, mostly because of that thing. If that was a 0, then you could move that to the other side. Yeah, you could do it. But with that not being 0, you can't move this to the other side because that doesn't have a y in it. There's just no way to, in general, there's not a way to separate. Now, if p of x was simple enough or f of x was simple enough, like f of x was a constant function, that would be okay. Because then you could do it over there, I think. Maybe not even that. But you could maybe separate, but in general, no, you can't. Okay. So how in the world are we going to do this? Okay. Before we examine a general procedure for solving that, we note that some instances that can be solved by separation of variable. And this is what I was saying before. Okay? If this f was 0, you can do it. For instance, if you had this, dy dx plus 2xy is equal to 0. Your p of x is 2x, your f of x is 0. Yeah, you can separate those two. Okay, first thing you do is subtract 2x from both sides, 2xy from both sides. So that gives you dy dx is equal to minus 2xy, right? Divide both sides by y and write this in differential form, dx, and here you have dy over y is equal to minus 2x dx. I think we can do that, can't we? Integrate both sides. What was that? Actually, I'm used to separating out the constant, but I'm going to leave that constant in there. Okay? What's the antiderivative of dy over y? Second? No, dy over y. The antiderivative of dy is y. dy over y would be log y, exactly. Natural log of y is equal to minus the antiderivative of 2x dx. I see mouths moving, but I hear nothing. X squared. And then we're going to need a c, or something like a c. And what I think I'm going to do now is exponentiate both sides. That's a perfectly good answer, but you could exponentiate both sides and have e to the log y is equal to e to the minus x squared plus c, right? That's legal. What's e to log y? Y. Why not? Okay. Whoops. Okay. Now, before we go any further, yuck. Okay. Rule of exponents. If you have same base, sum of two exponents, that's the same as e to the minus x squared, e to the c, right? Right? Multiply two bases, same base together, different exponents, keep the base, add the exponents, so you can do it the other way. But guess what? This e to the c is just a c. This is just a constant. So this could be written as some other constant. Let's call this one c1, and let's call this one c. c e to the minus x squared. There's your answer. Okay? By separation of variables. That was a review, folks. Okay? We didn't have to do that. They didn't do it in the book, but I thought it wouldn't be a bad idea to do it. Now, by the way, if written in this form, our p to the x here was 2x, okay, and our f of x was 0. I think we already mentioned that. But let's look at another couple of them. How about this one? dy dx is equal to y plus 5. Now that's not quite in standard form yet. If you put it dy dx minus y is equal to 5, yeah, that would be in standard form. E to the dy dx equal p to the y, p to the x times y, plus p to the x times y is equal to 5. Yeah, that's standard form. But can you use the separation of variables here? Answer is no. Okay. It almost looks like you could if you did this. dy over y plus 5 is equal to dx. Okay. frankly, I think that works, doesn't it? Oh, yeah, they say they're both linear and separable. Yeah, and we can do that. Pretty easy. Integrate both sides. This is log of y plus 5 is equal to x. And then you could exponentiate, or we could put a plus, let's call it C1, okay? Exponentiate both sides, and this would be e to the log of absolute value y plus 5, and that's equal to e to the x plus C1. We're going to do the same trick we did before, make that e to the x, e to the C1, and this over here gives us y plus 5. Now, do you need the absolute value bars anymore? I think not. Maybe it would be helpful, but I think you can get away without them, is equal to c e to the x. So yeah, that's doable to one parameter system. Right. But how about this one? dy dx is equal to, or I always want to put an equal there, plus y is equal to x. Now that's about as simple a form as you can get for a linear first order differential equation, but guess what? Even though it's a simple form, you sure can't separate the variables, can you? You got the x's on the outside, but you got a plus y you don't have anything to do with. You subtract the y from both sides, now you got x's and y's mixed, you can't separate them because they're combined by addition or subtraction, and those aren't separable by multiplication or division. So you're stuck. This one we can't do by separation of variables. Some linear first order differential equations you can, others you can't, like this one. So what is our method of solution? Okay? The method for solving something such as this hinges on a remarkable fact that the left-hand side of the equation can be recast into a form of an exact derivative of a product by multiplying both sides of the equation, okay, by a special function mu of x. Okay? They say it's relatively easy to find that function mu of x because we know what we want from it. So let's go back to our basic form, which is this. Okay. dy dx plus p of x y is equal to f of x. That was our basic form for a linear first order differential equation, right? Generally not separable by variable, though a few you can. This one you can't. Okay. Well, in general you can. Depends on the values for p and f. Okay. Now, what we're going to do is multiply the left-hand side of this equation or both sides of the equation by a special function mu of x. It seems like a strange thing to do. That'll be mu of x dy dx plus mu of x p of x y is equal to f of x mu of x. Okay? Looks like to me it just got a lot more complicated looking, doesn't it? Okay? Except for the fact that I'm going to just go somewhere else for a moment and pretend, let's just pretend we're somewhere else, okay? Let's take the function mu of x, y. Okay? Okay? We're just going to take this function because it sort of shows up here and mu times the derivative there. Let's take the derivative of this, d by dx of mu of x, y. Now remember, y is also a function of x. That's a good old take a derivative of a product. We use the product rule. And how does that go? How does that go? Okay, did I hear something like d by dx of mu times y of x plus mu of x dy dx. Is that right? Everybody agree with that? Okay. Now, this thing that we have right here is exactly that first term there, isn't it? Right? Now, what we have here, there's your y, okay? And if we could get this thing right here to be d mu of x equal mu of x p of x. If we could get that to be true, we'd be hunky-dory, wouldn't we? Okay? Let's rewrite that slightly. D mu is equal to mu of x p of x dx. So let's integrate the mu and integrate this thing, right? Would that be a legal move? See, all I did was write this in differential form, right? Okay. Well, that's what this is. You take the integral of a derivative, you get mu. So mu of x is equal to the integral Okay, I messed something up here. Let me find what I messed up. Right, let me see. Okay. I think I've done the same thing they have. Yeah, I've done the same thing. Yeah, okay, got it. No, I didn't. I see where I've messed up. I stopped too soon. Let's take off this. Sorry about this. Almost had it. Let's divide both sides here by mu of x, right? Okay. Now we've got it. Now we take the integral of both sides. Guess what this is? Integral of d mu over mu, log mu. And over here, the integral p of x dx. Okay? Well then, how could I lose the log? Say again? Okay, yeah, we're not going to worry about the C yet. Okay. How can I get rid of the log? How have we done it before? Today. Say again? Exponentiate. Take the e of this and the e of that. And suddenly I have that mu is equal to the e to the integral p of x dx. There's the e, there's the mu. And if I do this, then I have this being a perfect derivative, because this is d by dx of a product of mu and y. I know what y is. I know what mu is. How do I get what? Well, I don't know what mu is yet. I can get mu by taking the integral of p of x dx and raising that to making that the power of e. Okay? And then this side of the equation is that, and what I can do is multiply or write that as a differential form, and that mu that I calculated here times your y that we're looking for is equal to the integral of this dx, because you got that. And if it's doable, I can do that. Now that sounds like a lot of twisting and shouting and moving around, but guess what? It's all legal, okay? This is their equation 3. This is going to be the key that unlocks all of your linear differential equations that aren't separable. Even if they are separable, you can still do it, but why go to all this trouble if you can separate and solve that way? But if you can't, then this will work every time if you can do that integral, and most of the time. This is what we call an integrating factor. Okay, so linear differential equations and integrating factors, they actually come out pretty close to the same, especially first order. So that's what we're doing. So now, rather than doing the L in shield, we're doing the I in shield, which is the integrating factor. Okay. Now, they do a lot of stuff at the bottom and then say, don't remember it. I mean, no, don't memorize it. Let's just do it. Okay? Now, here's, again, they do a little step through. Remember to put the linear equation into a standard form, which is dy dx equal p of x, y, said it again, dy dx plus p of x, y is equal to some f of x. Get it into that form. Then separate out that p of x, go off to the side, integrate it. Just integrate it. Don't worry about any constants either, just integrate it. Whatever you get there, raise to that e to the that power. Okay? Then, that thing that you get, e to that power times y, d by dx of that is your left-hand side. Your right-hand side is e to the that thing that you just calculated times f of x. Okay? Separate those variables and you got it knocked. Okay? So let's do an example and we'll try to take it one step at a time. Okay? It's a pretty easy example. In fact, it's an example that we could do by separation of variables. dy dx minus 3y is equal to 0. Now that, yes, I admit we can do it separation of variables. We will. We'll come back and do that. But let's do it, since this is such an easy problem, let's do it by our integrating factor. First, locate your p. What's your p? -3. So your p of x is equal to -3. What do we do with that? Integrate it. Okay? So integral of -3 dx, by the way, would be what? Integrate that. Not that hard. Okay, let me write it this way. Minus 3 times the integral of dx. What would that be? Negative 3x. All right. Yes. Okay. Thought I heard you saying x. I want you to speak louder. So there's your integrating factor. So what do we do with it? We do e to the minus 3x. We put that as the argument for the exponential function. All right. Now, here's the magic. Okay. We multiply that. That's our mu. That's our mu of x. Okay? And we find out that when we multiply this together, this is saying e to the minus 3x dy dx minus e to the minus, let me put the minus 3y e to the minus 3x. Okay? And multiply that by this side, you get a 0. Okay? Now here's the magic. This is the derivative of the product of these two. This thing right here. Well, let's see. Yeah. It's the product of y times this. E to the minus 3x. I'm going to put the y in front. Okay. That is that. Okay. If you don't believe me, take the derivative. Okay. Derivative of y is dy dx times e to the minus 3x. Plus, product rule, y times derivative of e to the minus 3x dx be e to the minus 3x times the minus 3. And sure enough, that is. Yeah, that works. So this is the derivative of that, and that is equal to 0. So write that in differential form. D of y e to the minus 3x is equal to 0, dx. Integrate this. You integrate a perfect differential by the fundamental theorem of calculus. We'll integrate this too, by the way. And this gives us y e to the minus 3x is equal to some constant c. Isn't it? And now we can multiply both sides of the equation. I was starting to divide, then I decided to multiply. Multiply both sides of the equation by e to the 3x. And what's e to the minus 3x times e to the 3x? Second? No. Keep the base, add the exponents. Yeah, the base is e. Add the exponents. 3. No. Add the exponent. Negative 3x plus 3x. 0. And what's e to the 0? 1. Okay, so this goes away, and you have y is equal to c e to the 3x. Oh, yes, that's all. Sorry, I wish I could make it harder. Let's see, you do it the other way. Let's actually separate the variables. dy dx is all right to just say is equal to 3y, right? Agreed? Then divide both sides by 3y and write it in differential form. That would be dy. I'll take that. Divide both sides by y. dy over y is equal to 3 dx. Right? Integrate both sides here, and what do you get? log y is equal to 3x, and you can say plus c1 if you want to. Okay? Now when you're integrating the p of x, don't do a c there. But here, when we're doing separation of variable, we got to do that. Now, what do we do here to get y by itself? Raise everything, exponentiate everything. And this, by the way, is log y, or e to log y is just y is equal to, and we'll do our little trick here. This is e to the 3x times e to the c. E to the c1 is just some other constant, call it c. So that's going to be c e to the 3x. And that's exactly what we got here. So yes, this works. Okay? What's that? It's much easier separating variables. But I just wanted to show you this integrating factor does work. Okay? Just take it one bite at a time. How do you eat a 5,000-pound elephant? One bite at a time. Just take it nice and slow. Take it all the way through. Don't let it confuse you, get lost, and go for it. We can do that. Okay? Let's try another. This one won't be quite as easy, but it's not bad. Okay? In fact, I hate to do it this way, but it's so easy to. And even though I could do it, I want you to do it again. So we're going to do some of this all over again, but I think the practice of doing it is going to be worthwhile. Because there is a subtle little thing, difference. Maybe not all that subtle, but a difference here. This time it's equal to 6. So you don't have a homogeneous system. Where's our first step? What is your p of x? And what is your p of x? It's still negative 3. And what do we do with that p of x? We integrate it. dx. So we integrate that. dx. And what does that give us? Negative 3x. Just like we had before. And what do we do with that? What do we do with it? Okay, to get the integrating factor, there's one more step. The mu of x is equal to e to the that, e to the minus 3x. You exponentiate it. That's your integrating factor now. So what do we do with that? We multiply that by each side of the equation. So you got mu to the mu of x dy dx minus 3y, and we know what mu of x is. Let's not write it down like that. This is silly. Okay, write it. We know what mu of x is. Write it down. E to the minus 3x dy dx minus 3y e to the minus 3x is equal to, this time we have a 6 e to the minus 3x. Can't just say 0 anymore. But what does this left-hand side? What is that? That exactly d by dx of what? E to the minus 3x times y. That's exactly it. If you don't believe it, take a derivative of it. Derivative of this is e to the minus 3x times the minus 3y. There's that term. And the other part is e to the minus 3x times dy. That's that part. So yeah, this is exactly the left-hand side. The right-hand side, though, now is 6e to the minus 3x, right? Now, what I'm going to do, I'm tired of writing this over and over, So I'm going to write this as a differential like that. Okay? And now we're going to integrate both sides. Okay? So this becomes the integral of a derivative is, this is the thing, e to the minus 3xy. You got it. Is equal to, okay, I'll say -6 for your benefit. E to the -3x over 3. Since you already did the minus out there, so this becomes a -2. So this is -2 e to the -3x. Okay? And this time, guess what I'm going to do? This doesn't look fair at all, does it? If I multiply both sides of this equation by e to the 3x, that goes to 1. That goes to 1. Whoa, this isn't fair, is it? And that gives us a -2. Y is equal to, oh, I forgot to do my plus c. Sorry, plus c, but yeah. So that would be 2c minus 2c. Is that right? Let's see. What's dy dx? What is dy dx? If this is our answer, okay, we'll call that a C1 in there. If that's our answer, I hope I did it right. If that's our answer, what is dy dx? When you take the derivative of minus 2c, what do you get? 0, right? It's just a constant. Okay? So now we have dy dx is 0 minus 3 times y, which is minus 3 times a minus 2c. That's equal to 6. So it looks like 6c is equal to 6. Looks like c is always equal to 1. Okay? Now, something feels really strange about that. No, I blew it. When I did this constant here, I thought that was coming out way too strange. Let's back up a bit. Okay. Yeah, I got in too big of a hurry here. That came out way too bizarre. Okay. So you knew something had to be wrong there. Okay. Okay. I try to do too many steps at once. Let me back up one more. It was going so well. Okay. Right here is where I messed up. This becomes e to the minus 3x y, okay, is equal to minus 2 e to the minus 3x, right? We did that right, plus c. Now, I tried to get fancy here and call it e to the c. You can't quite do that yet, okay? It worked before, but not now. So what we do now is multiply every side of this one by e to the minus 3x. E to the, not minus, e to the plus 3x, e to the 3x, and e to the 3x. Ha! This will work. That goes to 1, so you have y is equal to, this goes to 1, minus 2 plus c e to the 3x. There's your answer. Okay. Now you take the derivative of this, dy dx, and that's going to be 3c e to the 3x, right? Now, you add that to, or take this one, minus 3y would then be 6 minus 3c e to the 3x, right? Add those together, add this to that, these two go out, you're left with 6, and you're left with 6. Yeah, that works without any other. Yeah, this one just fine, except that plus c, which usually catches us anyway. You can't make this an e to the c. It just doesn't work as well. So leave it a c, and that gives you your answer. So your answer is minus 2 plus c e to the 3x. Okay. That's the answer they get. They put their answer sometime in blue, which is harder to see. Y is equal to minus 2 plus c e to the 3x. And by the way, here, x can be any real number. Any real number. So, that's the answer. Yeah. Can you do this by separation of variables? Is that what you're asking? Don't think so. Well, wait. Let's see. Let's try it. If you say dy dx is equal to 3y plus 6, that would work, wouldn't it? Yeah, I think you can. So now we say dy, and since it is 3y plus 6, right, let's make that 3 times y plus 2. You all right with that? Okay. So let's dy over y plus 2 is equal to 3 dx. You buy that one? Yeah, this will work. Let's integrate both sides here, and what does that give you? A little louder. Sorry? Yeah, on that side, you're doing the easy side. I want you to do the hard side. What's that? Log n of y plus 2, and for right now, we'll put it in absolute value so we don't have any problems there, is equal to 3x plus c, right? Now you exponentiate both sides, e, and this time you can do these together. Let's call it a c1 here, e there, okay? And this gives you a y plus 2 is equal to e to the 3x times e to the c1. Let's just make that c, right? And now we have y is equal to minus 2 plus c e to the 3x. Yeah, I like that better. If you can separate variables, do it, you know. But you get the same answer. But I thought you needed to practice doing the other one. Because guess what? We're going to come to some that you can't do separation of variables. So if you don't know how to do this with the easy ones, you're jumping into it with the hard ones. It's going to be a real pain in the neck, right? No, none of this is a real pain in the neck. It's all fun. Okay. Now, they have a little graph. Now, not all of you have books yet, and I can't really draw this graph very well. I don't know if you can see it if I hold it up like this. Okay. Here is the graph. Here is the y is equal to -2. There's your x-axis, there's the y-axis. Y is equal to -2 is down here. And then the c's give you functions that go like that. Okay, so depending on what c you take, if you had an initial condition, any one of those lines that fits it, That gives you your exact solution. Rather strange looking figure, but that's where that minus 2 comes into play and all the other functions we talked about. Okay. I guess we'll start with the general solution, so that's kind of a blah, blah, blah type of a situation. We'll begin there next time and go from there. Let's see if we got enough for some homework exercises. We hope we did, don't we? Okay, let's do some of the odds 1 through 23. And we'll hold off the initial value problems. You may not be able to do all of them, but do as many as you can. Any of the odds 1 through 23. Good deal? Okay. And remember, I've said it to most of my classes, so most of you have heard it before, except Matt. Monday is not a holiday for the 2-year college system or the 4-year schools either. It's only for K-12. It's supposed to say a holiday. We will be here, so we'll see you Monday. Okay. Because I know you have a little one at home. Is she in school yet?
No, not, starting this year.
Oh.
So in August.
In August, okay. Well, that'll be a whole nother experience for
Yes.
me. Yeah, okay. Okay. Good deal. Have a good weekend. I can say it now because I won't see any of you again, maybe. I've got a student